Well, welcome everybody, and I'd ask if you're in the back there finding seats, hurry on, we're going to start in a second. I'm Gregory Deierlein from Stanford University, and I have the pleasure to introduce today's keynote speaker. But before I get to that, I'd just like to spend a couple of moments to thank and congratulate Rui Pino, the other organizing committee, and the sponsors for this, what's turning out to be a really excellent conference, taking us to the wonderful city of Milan, and treating us to Turndot at La Scala. That's going to be long before we forget that. Wonderful time. You know, yesterday afternoon, actually in this room, Jack Maley reflected on the first 100 years of earthquake engineering, 1906 roughly to, say, 2006, the advancements made in seismology, engineering, and social science. And in the second half of that 100 years, was the introduction of computational modern computing technologies, formalization of the finite element method, and other techniques by which we simulate structures. But now to think what's going to happen in the next 100 years, and by the way, we're already 20 years into those next 100 years, and I think clearly computational simulation is becoming more and more important with really unprecedented and virtually unlimited high-performance computing technologies, coupled with information technologies, artificial intelligence, machine learning, that really allow kind of a synthesis of all sorts of the disciplines, really multidisciplinary research. So that brings me to introducing today's keynote speaker, Xinzheng Lu, who's a professor at Tsinghua University, has really been a pioneer in advanced computational simulations. Coincidentally, I was looking at his CV, and his professional career starts just about the beginning of our second 100 years, roughly 2005 when he became a professor. But he's really kind of pioneered using high-performance computing with multi-scale modeling, going from detailed models of components and materials up to large structural systems, and then more recently coupling that with physics-based earthquake simulations to take buildings in the urban environment to really simulating cities and ultimately getting to these important questions of urban resilience. He's an incredibly energetic researcher. That's an understatement if you know him. Incredible amount of work and publications compiled in a book that he published, Earthquake Disaster Simulations of Civil Infrastructure from Tall Buildings to Urban Regions. It's already in its second edition. Some of us are still thinking about first editions of something. But an incredible body of work. He and his research team are also incredibly generous at kind of sharing their knowledge, but also at sharing their computational software and models. In fact, some of those models we in the US in the Computational Center for Simulation for Natural Hazards, we've implemented some of Xinzheng Lu's models into our computational simulations for regional analyses. So he's been very impactful both in kind of distilling the knowledge in books and papers, but also sharing it in software. And finally, he's been an active collaborator and contributor to professional organizations, to editorial boards, and to mentoring a tremendous group of students that have come out of Tsinghua and are really setting the future. So with that, it's a real pleasure to welcome up Xinzheng Lu for today's lecture.
Okay, thank you, Professor Deierlein, for the kind word, and thank you, the conference organization committee, to invite me here to introduce the work done by me and my group. So the topic of my today's presentation is from simulation-driven urban disaster mitigation to generative AI-powered seismic design. So the outline of my presentation is about these 5 parts. The first is why we do the work, and number 2, how we can extend the nonlinear time history analysis from building scale to the city scale. And number 3, how we can extend our research from earthquake engineering to multi-hazard of urban area. And number 4 is how we can further use the generative AI to accelerate, to promote our seismic design, and finally the conclusion. So first is the background. So you can clearly see that my presentation contains 2 parts. Why I bring these 2 parts here? It's because, firstly, in many countries in China, we have a significant seismic risk. So we want to know what will happen if an earthquake comes, and where the risk is. And another question is that we are living in an aging population. We have lack of construction laborers, and who and how we can address these significant risks. So first, for the what and where about the significant risks, we need to do the multi-hazard simulation of real-world large cities. Such kind of simulation should be accurate, efficient, and realistic because the manager of the city are always some non-professional people. There have been some very good models to do the city-scale simulation, but many of these models are empirical models. So they are using the previous earthquake to predict the damage of future earthquake. However, for example, in China, we don't have an earthquake in the densely cities for many years, and we have a lot of new structures that never experienced any earthquake in the human history. So facing this question, we said, okay, maybe we can move to the physics-based model. So no matter what kind of city you are or what kind of building you are, you should follow the nonlinear time structure dynamics. So we can use the nonlinear time history analysis to analyze the behavior of a building of a city in an earthquake. And then when we're talking about the lack of construction labors, we can see that I'm structural engineer, and all the design work is very labor intensive. And how to improve the construction efficiency is a big problem throughout the world. Particularly for the design industry, we have the problem like no efficiency cannot satisfy the demand. We have a lot of design data, but a little of them have been used. And our design quality are higher rely on the engineer's experience. So if we can bring AI to give us some help, then we can improve our design efficiency. We can change the knowledge of design from the brain of the engineers to a fixed asset of computing code of the company, and also we can improve the design quality of junior engineers. Okay, so first I'm talking about the nonlinear time history analysis from building to city scale. As I mentioned that if we can do the nonlinear time history analysis of a building or a city, then it will be strictly follow the fundamental structure dynamics, so we can address the problem of new cities or new buildings. So when I begin my career on this topic about 20 years ago, at that time China started building a lot of super-tall buildings. Of the buildings, they are very, very tall. Their component size is huge. And we are facing very strong earthquake. So it became a critical challenge to us. And I'm thinking about why we do the nonlinear time history of the building. I think that our purpose is to quantify the performance of the whole structure and the strong earthquake. That means our numerical model should analyze the complex whole structure, and we can study the collapse behavior of the structure. If you're looking at the photo of this real-world structure, we can see that although we have many very good numerical models, but few of these models can be used to do the collapse simulation of this real-world big structure. So we propose that we can use the fiber beam element model and the multi-layer shear element model to do simulation, because both of the models are based on material constitutive law. So they are very adaptive to different material, different component size, different loading condition for the real-world structures. Many of you are very familiar with the fiber beam element, and we do some work on the multi-layer shear element. That means we have a shear element. We divide it to many layers, concrete or steel, so that we connect the micro-scale material behavior with the macro-scale bending or force, shear force of the component scale, macro scale. And we also developed some new shear element to have a better performance to simulate the behavior of the shear walls. And some of these models, as Professor Deierlein said, have already integrated in the OpenSea software. So finally, in 2010, we can use this model to do the collapse simulation of the tallest building in China. So this is the Shanghai Tower with a height of 632 meters. So we use fiber beam element and multi-layer shear element to simulate the component of this super tall building. And in addition to the animation, we can also study the detailed failure procedure of this structure. For example, the red line on the top is the input acceleration. The green line is the top horizontal displacement. The blue line is the top vertical displacement. And the yellow curves here are the internal stress or internal force and strain of this structure of different components. So we can clearly see that how the failure starting from the coupling beams, then go to the mega columns and the shear walls, and finally go to the outriggers. So it can help us understand the failure mechanism of this super tall building. Okay, so in addition to this simulation, we can actually use this technology for the design optimization of the real-world structure. So in 2011, Beijing designed to construct a super tall building with a height of more than 500 meters. And the design intensity of Beijing city is 0.2 G, so it is a very strong earthquake load. So we involved in this project from 2011 to 2014, starting from the selection of structural scheme to the design of critical component. So at the beginning, the design agency gave this kind of design. We called it a half-braced scheme. So they have the mega brace on the lower fall zone of this structure and remove this mega brace for the upper fall zone of the structure. And we found there's a lot of problem for this structural scheme. For example, in the surface between the mega brace and without mega brace, there will be a weak point and induce the collapse of the building. So when we find the weak point of the structure, then we can work together with the design agency to optimize the design. So after the optimize, we get the four-layer braced scheme. We can increase the collapse margin ratio to about 15%, but at the same time, sell material about 11%. So this 11% of material is 84,000 tons. So it is quite a lot of money. So this optimization is quite welcomed by the design agency. And furthermore, from our simulation, we can find that, okay, the failure always happens at the zone 6 of the tall building. So this will be a critical part of the structure. So we can increase the shear wall by embedding some steel braces to increase its strength and ductility. And we do the collapse simulation and find that such kind of embedded brace only increase the steel consumption for only 0.1%, but can increase the collapse margin ratio to about more than 12%. So it is a very efficient way to improve the collapse resistance of this tall building. So when we finish the two super tall buildings, we think that we can do the nonlinear time history analysis, why we cannot try to do a nonlinear time history of a city. So about 17 years ago, we have the beginning of this idea. Some of us say, okay, this is a very crazy idea. Why? Because for a single building, we have very detailed structural information. And no matter how complex the structure is, it's only one building. But when we're talking about a city, we have very limited design information. We cannot get the design drawing for each building. And we have hundreds of thousands of buildings to analysis. So we said, okay, at that time, we don't know how to modeling that. We don't know what kind of computer can solve this problem. We don't know how to display the result, and we even don't know who will use the result. But so Newton said that we should stand on the shoulder of giant. So there's two giants there. One is the AEBM by FEMA, and another is IES by Professor Horry. So we based on these two models, we proposed the city-scale nonlinear time history analysis method. This method have get award from award patent from China and the United States. So this method, it can strictly follow the fundamental of structural dynamics, and it can accurately represent the characters of different buildings and the different ground motions. So the key problem of this method is how to establish the structural dynamics model for each building and how to determine the parameters of each building. So we propose this multi-scale structural dynamics model. That is, for conventional building, we select the moderate fidelity model. We use the MDF shear model for frame structure or masonry structures, and use the MDF flex shear model for tall building. Of course, we have some special buildings, and we can use the high fidelity model, use the refined fidelity model to do the simulation. Another challenge we are facing is that we have two determine the parameters of the MTOM model based on the building inventory because we don't have the design drawing of each building. So we propose a method that based on the empirical formula, we can determine the story stiffness. Based on the design code, we can get the design strength, and based on test data, we can get the actual strength and actual ductility of the building. Because time limited, we cannot go to too much details. The detailed work can be found in the paper shown at the bottom of the slider. And for the computational challenge, we can see that although you have a city with thousands of buildings, but you buy a GPU with about $1,000, you can have hundreds of cores. So if you let each core to do a computing for each building, you can get a very high acceleration ratio. So you can use a very low price computer to do the simulation. This kind of city-scale time history analysis has many advantages. First of all is that it has a high accuracy. Because it's a physics-based model, you can easily do a lot of comparison because you can compare with a test about the interstory behavior. You can compare with the monitoring data to know the drift, and also can compare with the actual earthquake to predict the damage. And the second advantage of this method is that it's very good for visualization. In old days, we do the earthquake damage prediction. We only show the tables or numbers, but this is very hard for no professional people to understand. Now we can know the totally dynamic response of buildings, so we can use the three-dimensional animation to show the managers what will happen, animation what will happen. For example, this is what we did in 2016 about Beijing CBD area. So this is a tall building in Beijing CBD. Some conventional tall buildings, we use MDF model, and some very tall building or very special building, we use the refined finite model. We input the Sanhe Pinggu magnitude 8 earthquake, and we can clearly show the shaking of the tall buildings. We not only to know the shaking of the building, we can also know the damage of the building. So here you can see the blue means no damage, green means slight damage, and yellow means moderate damage. So we can know the damage of each building on each story at each moment. So it's very easy for people to understand. And further, if we combine this dynamic simulation result with some photorealistic three-dimensional model, we can give something like a movie to show the shaking of this city. And it's very easy for no professional people to know what will happen to their city if an earthquake comes. And another advantage of this statistical time history analysis, it is very easy to consider or connect with other simulations. For example, if we want to know the interaction between the buildings and the site beneath the buildings, that is we call the site-city interaction, we can use the MD model together with the spectral element soil model together. So here we can show that when there is a site, they have the densely tall buildings, and the reaction force from a density tall building will have significant effect on the ground motions. And this method can also be used for the complex terrain. So this is the new Beichan city. We can not only shaking the buildings, but also can shaking the mountains. We can see the deformation of the mountains. We can know why the acceleration on the top of the mountain will be stronger than the foot of the mountain. So it can help us do a lot of study. The fourth advantage of this method is very good for resilience assessment. Now everybody talking about resilience, but when we start resilience, we need more EDP, engineering demand parameters. We not only need interstory drift, we still need, for example, peak flow acceleration or radial displacement of each story. But with nonlinear time history analysis, we can know all these EDPs of each building. And when we combine it with a good performance group and a good data model, then we can get a better prediction for the resilience of the city area. For example, we can combine the building information model with the FEMA P58. Then we can know the damage on each component, and we can go inside the building to see what happens to this building. And we can further extend it to a city scale. This is what we did for Beijing City. We do a city scale seismic resilience and recovery simulation. We simulated different earthquake scenarios, and also we can consider the constraint of workers, because there are so many buildings are damaged, we don't have sufficient workers to repair all these buildings at the same time. So we optimize the repair recovery procedure, and you can see that the worker will firstly concentrate at the center of the city and then distribute to other area to make the city recover as soon as possible. Okay, and then this technology has many applications, not only before earthquake for the disaster prevention, but also can after earthquake for emergency response. A typical example is what we do together with CIM Center for the San Francisco Bay Area. The Professor Steve Mahan helped us to connect 1.8 million buildings in San Francisco Bay Area. And also, this is the magnitude 7 earthquake generated for the Howard Fault. So with this scenario, each building have different ground motion. So we can clearly see the shaking of the entire San Francisco area subject to this earthquake scenario. It clearly shows the movement and even the damage of each building in the downtown San Francisco area. And with this simulation result, we can further to study the loss ratio and the repair or rebuild time of each building. So it set up a very good foundation for our study on resilience. And another advantage of this method is that it can be used to study some secondary disaster. For example, the falling debris. You can see that this is some movie taken from Mexico earthquake or Japan earthquake. The building is still standing there, but the debris falling down from the buildings and may kill people. But how to predict this falling debris, it will be a very critical question. However, with our city-scale linear time histories, we can solve the problem. So we first do the analysis, then we know the shaking of the building, we know the interstory of each building, and also know the velocity and acceleration of different stories. And with this, we do the experimental, know the failure criteria of the falling debris, and simulate the distribution of the falling debris on the ground. Then we do the evacuation study to know how about the falling debris on the ground to change the evacuation speed. So here is the animation shows that this is the Beijing CBD area. So we have earthquake coming, and you can see the red ones are the falling debris from the building. So we can know that how about the distribution of the falling debris in this case. And with this falling debris, we can use it, for example, to select a better emergency shelter place, consider the falling debris, or we can do the evacuation simulation, consider the falling debris. You can see that because the existence of falling debris, the evacuation time will be changed quite a lot. And this technology has been used in many Chinese cities. Here is just some examples. And one of the recent, I think, very interesting application is in the Beijing Olympic 2020 Beijing Winter Olympic Games. So we use this technology to assess the seismic risk of the Olympic regions and get a very good comment from the Olympic Organization Committee. Okay, this technology can not only be used before earthquake, but also can be used for post-earthquake assessment. In traditional ways, we have earthquake, we use a lot of empirical models to predict the seismic intensity and predict the building damage, and they have a lot of uncertainty there. Now, we can directly use the recorded ground motion and do the city-scale time history analysis to significantly reduce the uncertainty. So we developed this code platform we call the real-time earthquake damage assessment using city-scale time history analysis. We call it REDACT. So we use the very large strong motion network in China. Every time earthquake happens, we get the recorded real ground motion, and we input it to the building inventory, to the city-scale time history analysis, and we can know the damage of the disaster region. So here you can see the right figure. The different circle represent a different location of the station, and different color represent a different damage stage. So we can clearly see how much damage of the area was suffered and where the most severe area is. So this is one of the typical applications of this technology. In 2017, China have a magnitude 7 of Zhujiagou earthquake. So after the earthquake, some agencies use the conventional way to predict that this earthquake will result tens of thousands of building collapse. And we use our model to predict this earthquake will have very small possibility of building collapse. So when we read this result, they are quite surprised because it is a magnitude of 7 earthquake. How it is possible? But after 1 month, the site investigation shows that the collapse ratio is only about 0.1%. So it is agree very well with our prediction. So this method has been used by Chinese Earthquake Network Center and be used to do the seismic damage assessment, both for domestic earthquake and also the earthquake in other countries. So on the bottom, we show the 3 earthquakes happened in the United States and Japan. And this is our assessment result just after the earthquake. You can see the different color means different damage state. Okay. So then we want to extend it not only about earthquake, but also considering different hazards. So when we're working on city, we're always facing the problem that how many systems we want to build up. We need to build a system for earthquake, another system for wind, or another system for fire. So they want a platform for all these multiple hazards. And also, the city not only worry about the regional scale, but also worry about some important buildings. So they have multi-scale problems. So we think, okay, why we do called it a city information model. So we combine the GIS model and the building information model together. And with this city information model as the database, we do the physics-based hazard simulation. And this result can be served in many different purposes. This is a typical example that we set up the city information model of the entire Tsinghua University campus. We have the entire campus model and also some detailed model of important buildings. So we can do the regional scale simulation for earthquake, fire, wind, even COVID, and also the building scale simulation for different hazards. Here is one of the example that how we do the physics-based fire simulation with this at building scale with this city information model. So we start from the building information model, then we extend it to the FDS of fire simulation. We can get a fire scenario, and we can also do the evacuation simulation in such of cases. And we can also do the physics-based fire simulation at the regional scale. So in the older ways, in the empirical fire spread model have many problems. So we propose use a physics-based fire simulation. We consider the thermal effect, radiation effect of fire, and the 3D evaluation of the buildings. So here is a typical example that these 2 towns have fire in China, and our simulation result agree quite well with the actual disaster. And the advantage of this physics-based model is that we can very easily to consider one disaster with another. For example, we have a physics-based fire model, we have a physics-based earthquake model. We can connect them together, then we can do the physics-based simulation of fire following earthquake. And they have many advantages over existing models. Here is an example that what we did a simulation for the Wajima city in Japan in January this year. We can see that we can simulate the entire fire spread procedure, and our prediction result agree quite well with the actual fire spread. And because we have a physics-based model, so we can not only show the fire spread result, we can also show some very realistic, for example, the smoke of the fire. So we can see this is we did for Taiyuan City, fire following earthquake. You can see that the simulation result is quite similar to the real-world fire following earthquake. And we also use this technology for Beijing Second Administration Center. So on the top is the original plan. We just show to the mayor, say, okay, your original plan, the fire initiation place is quite close to your office. And you're looking at the down one, the revised plan, the office will be quite safe. So this revised plan is quickly accepted by the administration. So it is the advantage of why we have this realistic simulation result. And we can also do it for wind. The conventional empirical model for wind have many problems. So we can combine the city scale time history analysis, dynamic analysis of buildings with the city scale large area simulation. So we can input the dynamic wind load to the building to get a dynamic response of these buildings. So we do it for the San Francisco city. We have these building models. We generate the CFD simulation. We compare our CFD simulation with the wind tunnel test. And then we can get how the wind goes through the tall building in the San Francisco Bay Area. And subject to this dynamic wind load, how the tall building of San Francisco downtown will shaking. It is very interesting to find that because the overlap of different buildings, the wind load on the building is quite different from the design load. And also we find that the dynamic response of this building is quite different from the design code we specified in our design specifications. And we can also even do it for the COVID-19. On the Monday, we have a very beautiful song in the opening ceremony about fighting everybody against time. And in 2020, January, at the breakout of the COVID, we still have the real-world challenge for fight against time. We are ordered to construction a hospital only in 10 days from nothing to in service. And this is a very challenging question, and one of the problems is how to reduce the infection risk caused by the harmful air. And because the time is very limited, we should be very efficient and very accurate. So we use our proposed method so we can finish the design optimization in hours. So in January 28, we finished the design optimization of Shenzheng Hospital in Wuhan. The next day, we finished the design of Ditan Hospital in Beijing. And then the next day, we finished the Shenzheng Hospital in Wuhan. So we can finish the design of each hospital in 1 day, and the total sick bed we served is more than 10,000. So I get a very special award from the Ministry of China. I think this is a very important award to me because we really save lives. And then today, a lot of people are talking about using the AI to further improve our disaster simulation. And we always suffer the problem that we don't have sufficient data to training our AI. So we propose that we can use our physics-based model to generate a lot of simulation data and combine the real-world disaster data with simulated data to do the machine learning so we can get a better data-driven simulation for the city. Our group also do some work from the data acquisition to the displaced measurement and also to the computing efficiency with AI. But because of time limitation, I don't have time to introduce them. You can see the paper in the slide. Okay, then we come to the presentation about how to use the generative AI to do the seismic design. So the first question is, what is the generative AI? Generative AI, you can see the animation on the screen. So the bottom right four faces are the faces generated by computer with the faces on the four faces on top and the faces on the left. So you can see this animation clearly shows the critical features, characters of generative AI. Means after AI learns so many data, they can generate a new thing, a new face. And the new face is so realistic, you cannot identify it from the real-world people to the AI-generated people. So when I see this animation 7 years ago, I recognize that, okay, there will be a revolution in our industry. Why? Because we are structural engineers. The most important outcome of our work is the design drawing. No matter it's a face of people or a design drawing, it's only a picture to a computer. So if AI can generate a human face looking like a real-world human, why AI cannot generate a design drawing looking like a real-world human design? So that is the fundamental idea that why we can use the generative AI to help us to do the structural design and make the design efficiency improve quite a lot. And there's 3 key algorithms to help us to generate this AI-based design drawing. Engine 1 is, we call it engine 1 is the generative adversarial network GAN. Engine 2 is the graphic neural network GNN, and engine 3, we call it diffusion model. The equation of this algorithm are shown on the slider, because I think after 2 days of very productive conference, everyone is quite tired. So I don't want to talk about too much physics, mathematics here. I just want to show the fundamental of this algorithm. So first, what is the generative adversarial network GAN? Its working mechanism is just shown like this picture. So it has a generator. The generator is something like this bad guy. It always creates some pictures to following the real-world picture. The discriminator is like the placement. It will identify this picture is generated by the generator or it is the real-world picture. So the generator and the discriminator, they fight against each other and keep optimization. And finally, it can generate a picture that looks as good as a real-world image. So that is, we can do it for the AI-powered design, that we keep input the design drawings to the GAN and the AI to learn how to generate a new design. And after the optimization against each other, they can generate a new design that looks like the real-world human design. The second algorithm is talking about GNN. What is a GNN? The data should start from a graph. Graph is a topological structure made with node and edges. The GNN is a neural network working with a graph. And there are several algorithms can be used for the structural design. The first one is we call the edge classification problem. What it means? It means that we have two objects. We want to know the relation of these two objects. So we can use this God of Lord. We all see the movie of Lord of the Rings. We can use it example. So we can see that we can separate these people to the wizard side or Sauron side. So this algorithm can help us for the structural design, for example, the layout of the beams. So we can make the link between every two columns in a structure. And we let the AI to learn the existing frame design. Then the AI identify, OK, this link is the real-world beam we need. And this link, we don't need to be a beam. So with this algorithm, we can finish the layout of the beams of frames with AI-powered design. Another algorithm is the edge feature prediction of GNN. Means that we have two objects. We need to predict the value between the two objects. We still use Lord of the Rings as an example. We can say, OK, even these characters belong to different sides. They have loyalty between these different characters. And this algorithm, we can also use it, for example, to lay out of the shear wall. So between any node, any two nodes, we want to lay out the shear wall. They have several possibilities. If it is a continuous shear wall, the feature will be 50%, 50%. If on the left side is a shear wall, the right side nothing, then it will be 50% and 0. If both sides have shear wall but at a door in the middle, the edge feature will be 30% and 30%. So after AI learning, they predicted the feature between the two nodes, and then AI know how to lay out the shear wall. And also the diffusion model that we can remove the noise from the drawing, and finally the left component, the left pixels, will be our final design result. OK, so this algorithm, then the next step is establish the database for a data set for AI to learn. So we establish maybe the world's largest structural design data set for the data for the AI training. So currently, AI can do this work. We can do the vertical component layout, horizontal component layout, cross-sectional design, and even some special component like base isolation design. Because today we are talking about earthquake, so I first emphasize on the layout design of shear wall. So how human design the shear wall in the real world? So that is what engineers do. So firstly, the architecture has this architecture planning and also the design condition of the building. So for the first step, we lay out the shear wall at the given location by the architecture. And then we consider the design condition. For example, we have the design intensity, and we change the total area of the shear wall. And then we do the structural calculation to predict the structural behavior to satisfy the design code. And finally, we use some empirical rules to further improve the details of the shear wall design. So we simulate the human design procedure and propose the algorithm to solve this problem. First is how to lay out the shear wall according to the architecture layout. So we propose the integrated design method for shear wall layout based on different algorithms. The details can be found in these papers. And this is what we get. So on the left is two buildings architecture layout. So the green means window, the blue means door, and the gray lines means the walls. And on the right is the layout of shear wall. Some of the shear wall is done by human, and some of the shear wall is done by AI. So can you identify which one is done by human and which one is by AI? Okay, so here is the result. So in 2019, when we first get the result, we are so excited. We say, okay, this is something that interesting, we can go on with it. And then for the next step, how we consider design condition, for example, the design intensity. So we proposed to embed text feature fusion algorithm to do the generation. So here is the example. So here is the architectural drawing. So if we want to do a structure with the PGA of 0.1 G and a height of 50 meters, then the AI will generate shear wall like this one. So you want to increase the height to 50 meters to 100 meters, and after several seconds, AI will give an AI shear wall generation like this one. So if you want to move this building from 0.1 G to 0.22 G, then AI will generate a shear wall like this one. You can clearly see that AI knows how to generate a design following the design conditions. And third, we want to control the structural response. So we change the structure of the GAN. We put the physical estimator into the GAN. The physical estimator to optimize the structural mechanical performance. And this physical estimator is a Resonate 18 surrogate model to predict the maximal inter-story drift ratio. Okay, so here is the design result. So if we only use the data-driven, you can see that the AI-designed shear walls have less shear walls than the engineering design. And with the mechanically enhanced design, the designed shear wall is quite similar to engineering design. And the AI-designed shear wall can satisfy the inter-story drift limit in the design code. And finally, we want to improve the detailed design of the AI so we can introduce the attention mechanism to improve the design result. So here is the example. So without the attention mechanism, you can see that the shear wall near to the elevators is not good. But with the attention mechanism, the shear wall around the elevator is much better, and also the structural performance is also much better. And then we can also use the technology for the horizontal component layout. For example, we can do the frame bin layout. As I mentioned before, that we can use the age classification problem for GNN to lay out the bins. Means that we can classify the different links between the columns to be bin age or no bin age. And we propose, we call it the age feature enhanced GNN. We call it graph SF. We can see that with this algorithm, we can accurately predict the bin layout for this case. And other algorithms in the literature can correctly learn how to do the bin layout arrangement. And here is some real-world case. So on the left is two real-world frame structure, the arrangement of the columns. And on the right are the layout of the bins. Can you identify which one is done by AI and which one is done by engineer? And here is the result. The AI design is almost about 95% accurate compared to human design. And now we can further extend to the bin layout to shear wall structure, but the problem will be more complicated. Because you have two columns, there's only one bin. But you have two shear walls, they have infinite possibility of arrange bins. So we propose an algorithm for the shear wall bin layout, and also there's the example. So on the left is the two vertical component layout, and on the right is the bin layout. The blue line, the green line means the bin. So can you identify which one is done by AI or which one is by engineer? So it also can get a very similar result. And after the layout design, we can do the cross-sectional design. We propose what we call the rule-embedded generative adversarial network. We can consider the design conditions, we can consider the design drawings, and we can also consider the domain knowledge to generate the cross-sectional size of the components. Here are the two examples. For example, on the top, AI can generate the section of the columns, and with the knowledge embedded, the column will be symmetric. And on the bottom, the AI can generate the thickness of shear wall, and with knowledge embedded, the shear wall satisfies the consistent thickness. And we select 71 tall buildings, do the blind test to 56 engineers, and about half of AI design can successfully be judged as engineer design. And also here is the typical building. We can see that the section determined by AI is quite similar to the section designed by engineers. The two buildings have similar mechanical performance. The AI design even has smaller material consumption, and the AI design can finish the work in 12 seconds, and people need to work it for more than half an hour to design this building. And also, we can do it for some special component design. For example, we can do it for the base isolation design, so we can combine the discriminator, physics estimator, and rho evaluator together to generate the base isolator. So this is an example. We can see that we determine the base isolator. All the isolation bearings have some diameters, and the building satisfies the design code, but not too conservative. And also the design efficiency is improved about 60 times. You can finish work just in 30 seconds. And also we can, for example, do it for the BRB brace for the strengthening of structure. But the layout of the BRB braces need to consider requirement of architecture, and the architecture requirement is quite difficult to model. So we use the AI to learn the existing drawing data and then to predict the feasible position according to architecture requirement. So here we have the two-stage design procedure. First, we use generative AI to know the feasible layout of the brace, and then we do the structural optimization to further get to the final location, the final section of the BRB. So here is the example. After the two stages of design, the brace can be finished, design be finished in 15 minutes and totally automatic. And also we can use AI for the optimization, because sometimes AI just don't give a very good result. Sometimes it just don't have a very good training data. So we can use AI to do the, we call it intelligent optimization. Means that we use the big data and use the learning to do the optimization. What it means, for example, when we do the dynamic assessment or the material usage evaluation, we can use the AI as a theoretical model to accelerate the procedure. And even after the optimization, we can use the data, optimize the data back as training data to make the AI more powerful. The key technology here is we call it graph representation and the GNN algorithm for the entire structure at macro, middle, and macro scale. Means we have a building. We have 3 levels, 3 scales of information. First is the macro scale, for example, the sectional height, sectional thickness. The second is the medium scale, means the topological arrangement of structure component, and the macro scale, for example, the design conditions, the seismic design node. So with this algorithm, and then we can use AI to generate, for example, we can use that generate more than 1,000 buildings, and use the 1,000 building to train the GAN, and then we can use it to predict the structural response. And here is the result. We can see that the prediction is better than existing models, and the structural response can predict in less than 1 second. And we can also use this method to predict the material usage. So with sufficient data to train the AI can work like an engineer with 30 years of experience. They can know the material usage within a second. So this is how we do the work. First, we have AI, so we can design as many buildings as we need. So we designed 3,000 buildings, 300 buildings, and also embedded domain knowledge to the neural network. And now we can predict the material usage and the time is just 0.36 seconds to predict material usage. So we combine the AI calculation of seismic response and evaluation of material usage. We can do the structural optimization. For example, for this case, in 10 minutes, AI can generate a result past the seismic design. If you use traditional finite element, even after 2 hours, they still can get a good result. And we can also use the optimization algorithm to further improve the data set quality. Why? Because if you have a low-quality design data to training the AI, then you get a bad AI, and bad AI get bad design. But after your optimization, you get a very high-quality data set. And use this high-quality data set to train AI, you get a good AI, and good AI generate good design outcomes. So here shows the result. After optimization, that our data set have a significant improvement of physics laws. And the result generated by AI also have a very significant change in the physics laws, means the structural performance. So after we finish all this work, we want to not only publish papers, we want to this system can go into real-world service. So we developed an intelligent design system based on AutoCID and a cloud platform. The website is ais.com. Everyone can use it freely. So the engineers just use AutoCID to predict all this, to prepare all the information they need. And then they upload the design demand to the cloud computer. And the cloud computer finishes design and send back the design result. So this work can be very fluently embedded in the daily workflow of the engineers. So with this system, when the engineer have an architecture drawing, in 1 minute, AI will generate 3 or 4 different design results with different algorithms, including the shear wall design, the beam design, the sectional design, and the material prediction. Here shows the result. And if you are not happy with the AI design result, you do a click, and in 3 minutes, you will get an optimized result. And here shows an example that with this one-click operation, you can get a very better optimization. So here is a case. It is a real-world case. You can see that on the top is the engineer design, and the other 3 figures is the AI design using different algorithms. All the designs are quite close to engineer's design, but different algorithms generate different results. And you can check the design outcome, AI design outcome, and find all the AI design can meet the design code. It is not only the inter-storage drift ratio or vibrant period. We can check all these factors, and all these can save the design code. And the AI design has similar material consumption as the engineer design. You can see that generally within the 10%. So the system is online for about 1 year. We have 100 design institutes are using the system. And this system has been finished more than 1,500 design cases. If you look at AI as a real-world engineer, maybe this engineer will be the most experienced engineer in the world. So when I prepare the slider, I just take a look at the background menu system, and this is a typical case. So the top ID is the number of the building, the system design. Here is the date. The user used it on Monday, and the bottom is the design result. So they have 2 pictures, means they have 2 standard stories. And finally, on the right, the color is in black, means that the user finally accepts the design result of the diffusion model, and they download the model for his further usage. So you can clearly see that the AI can really do this work and really used by engineers. Okay, so finally come to the conclusion part. I have mentioned that we have the significant risk, so we want to know what and where the risk is, and we have the lack of construction labors, so we want to know who and how to solve the problem. So maybe in the future, we can use the digital twin cities to identify the problem to get intelligent disaster prevention And we can also use the generative AI to solve the problems and to get an intelligent design. Okay, so that's all for my presentation today. Then finally, I need to acknowledgement for all this support from the mentors, friends, and funding agencies, and many mentors have passed away, leave us forever. I need to thank all these co-authors to write the paper together with me, and particularly for all the students that most of the students are actually done by them. Okay, so that's all for my presentation. Thank you very much.